Hi everybody, and welcome to week 2 of our exam countdown. So any of our full members, you will see that I have put a link to the week 2 exam countdown in the chat, and you will, from going to that link, you will see all of the material that you should be looking at in week 2. So week 2, we're going to concentrate on complex numbers, and we will be doing the same next week. So you'll see on the screen, I'm going to jump straight in. You will see on the screen, I have just written out a list of things that sometimes comes up in complex numbers questions. Now, I won't be able to get through every single thing on that list today, but as I mentioned, our full members, you will have access to the videos and the links from the Maths Tutor website. And anybody that's not a full member yet, I will also be putting links to the videos in your chat, so you'll see them popping up on the screen there as well. So I have 2 videos linked for this week that you will be able to access. The first one is finding the modulus of a complex number, and the second one is looking at the conjugate roots theorem. So I'll refer to those as I'm going through today as well. So to start with, this list on the left-hand side is our list of things that may come up in complex numbers questions. It's not an exhaustive list. There are some things that have been left out, but most of the things should be there. So today, we're going to hopefully get through, we're going to have a look at what exactly an imaginary number is. So where do they come from? We're going to have a look at division of complex numbers, and we're going to maybe look at 1 or 2 questions from the exam papers. That will also bring conjugates into the mix, and we're also going to look at a very, very important aspect of complex numbers, which is changing to polar form. Okay, so to start with, what exactly is an imaginary number? So if we look at the right hand side here of the screen, I've written the square root of -1 is what we call an imaginary number. Okay, the reason the square root of -1 is an imaginary number is we can't find the square root of a negative number in our real number system. So if you put the square root of -1 into your calculator will tell you it's a math error. It simply cannot be done in the real number system. So to get around that, we give the square root of -1, we give it a name, we call it I for imaginary. Okay. Also, if we look at it, if we think about it, if we square both sides, so if we square the left-hand side of that equation and square the right-hand side of that equation, well, on the right, we end up getting I squared. And on the left-hand side, squares and square roots are exact opposites of each other. They're inverse functions of each other. So they basically reverse each other, or one undoes the other. So what happens is the square root and the squared, they cancel each other out, and we're left with -1. So these are 2 very, very important facts that come up in complex numbers. I is the square root of -1, and I squared is equal to -1. And we're going to be using this fact in particular when we get on to division of complex numbers. Okay, so just to look at, first of all, we're going to look at where we might end up getting the square root of a negative number in a question. So you might remember from last week, we looked at some quadratic equations, and we said sometimes we end up getting 2 roots, sometimes we end up getting 1 root, and sometimes our roots are complex, if you like. So we're going to start off with a nice simple quadratic equation, x squared minus 4x plus 5 equals to 0. And what we're going to do is we're going to try solve that quadratic equation. Again, you might be solving it using guide number, but you will find that if you use guide number won't work in this instance, okay? Because our roots are not real numbers. So what we need to use our minus b formula. So if we just remind ourselves of the minus b formula, you will find it on page 20 of your log tables. So that's our minus b formula. And as we did last week, we're going to remind ourselves what's A, what's B, and what's C. So to start off with, A is going to be the number in front of the x squared. So right here, there's an invisible 1. That's my A. B is going to be the number in front of my x. That's going to be -4. And my C is going to be the constant at the end, which in this case is 5. So subbing into my quadratic equation then, what we have is x equals, So x equals minus b is going to be minus 4. So I'm making sure that I'm putting it in brackets just so I'm definitely not making a mistake. Underneath the square root, we end up with minus 4 squared minus 4 times a times c all over 2 times a. So that's going to be 2 times 1 in this case. So simplifying, what I'm getting is x equals minus 4 is going to give me a plus 4, plus over minus. And when we work out what's underneath the square root, we end up getting minus 4 when I square it is 16, and 4 times 1 times 5 is 20. So 16 take 20, we end up with a negative underneath the square root. And on the bottom line, 2 times 1 is just going to give me 2. So the big thing here, which we didn't come across in the real number system, is we end up with a negative underneath the square root. We cannot put that straight into our calculator, as our calculator will just give us an error. So what we bear in mind is what we said up here up at the top, that the square root of minus 1 is equal to I. So I'm going to change minus 4. I'm going to rewrite that. We know that minus 4 is just 4 times minus 1. And we know from our rules of surds that we can split the square root up so that it's just the square root of 4 times the square root of minus 1. That can be done because the 4 and the minus 1 are multiplied underneath the square root. We all know that the square root of 4 is 2. And from what we said up here, we know that the square root of minus 1 is now what we call I, an imaginary number. It doesn't come into the real number system. So back to my minus b formula. Now what I have is x is equal to 4 plus over minus. Instead of the square root of minus 4, it's going to be called 2i, and we're dividing that whole thing by 2. So for my two answers, what I'm going to end up getting is x equals 4 plus 2i all over 2. And for my second answer, that uses the minus, x equals 4 minus 2i over 2. We don't really like to see fractions in complex numbers. So what we're going to do is we're going to divide everything across by 2. In other words, we're going to divide that bottom 2, the 2 on the bottom line, into the 4 and the 2 on the top line. So that's going to give me x equals 2 plus I, and over here, x equals 2 minus I. So what have I done there? I've divided the 4 and the 2 on the top line by the denominator of 2. So I'm getting 2 plus I and 2 minus I. So what you'll notice about these two answers, they're very, very similar. The only difference is the sign in front of the imaginary part. Okay, these are what we call conjugates of each other. So I've mentioned my video in the chat, the conjugate root theorem. That will give you another bit of information. So if you click the link, that will give you another bit of information on conjugates and on roots of quadratic and cubic equations. It's not a coincidence that they've turned up as conjugates. It's not a coincidence that the only difference is the plus and the minus in front of the I. That's always going to be the case once the coefficients of my quadratic or of my cubic are real. So what do I mean by real? And what do I mean by coefficients? What I mean by coefficients is the numbers in front of the x squared, the number in front of the x, and the constant at the end. They're all real numbers, okay? There's no imaginary numbers in there. So once those coefficients are real, the conjugate root theorem applies. In other words, my roots, my answers, are going to occur in conjugate pairs. They will be conjugates of each other, okay? So just to go back to our list, we mentioned that we're going to talk a little bit about imaginary numbers, and my two roots that I got down here, my two answers, they have an imaginary component to them. So they have the imaginary component is the I part at the end, but they also have a real component. The 2 at the front is the real part of the number. So that's where complex numbers gets its name. Complex numbers are composed of a real part and an imaginary part. So the 2 is your real part, and the I, or the one I at the end, is your imaginary part. Okay, so we're going to look a little bit more at conjugates of complex numbers, and we're going to do that by trying an exam question where we're asked to divide complex numbers. Okay, so you might be familiar with this question. It's from the 2021 paper 1, and it is question 1, just part A that we're going to have a look at. Okay, so we will always see complex numbers, and I should have mentioned this at the start. We will always see complex numbers in paper 1. Comes up most years as 1, if not 2 questions. Okay, so question 1 asks us 4 minus 2i over 2 plus 4i is equal to 0 plus ki. And they're telling us here, so just the information in the question is telling us that k is an element of z, and we know that z are our integers. So our integers are our positive and our negative whole numbers. So in other words, we're expecting that when we get our answer, when we find the value of k, that k will either be a positive or a negative whole number. It shouldn't be a fraction. It shouldn't be a decimal. And you're also seeing here, I squared is minus 1. We spoke about that at the start. That's basically just telling us where the imaginary numbers come from. And that if I see an I squared in my answer, I will always change it to minus 1. I should never leave an I squared in my answer. Okay, so if we concentrate on what they're actually asking us in the question, they're telling us that when I divide 4 minus 2i by 2 plus 4i, I end up getting this complex number. It shouldn't have a real part. Its real part should be 0, and its imaginary part should be ki, and it's k that we're looking for. So we're going to start by writing out the division. My division is 4 minus 2i over 2 plus 4i. Okay, how do we divide complex numbers? We divide complex numbers by multiplying above and below by the conjugate of the denominator. So by the conjugate of this bottom number here. Remember, a conjugate is one where the imaginary part has an opposite sign. So the conjugate of 2 plus 4i is simply going to be 2 minus 4i. And it's fine to multiply the top and the bottom of the fraction by that, because I'm essentially just multiplying the complex number by 1. I have the same thing in the numerator as I have in the denominator, so I'm essentially just multiplying the fraction by 1. Let's see what's going to happen on the bottom line when I multiply a complex number by its conjugate. So we're going to work out what the top gives us by multiplying 4 minus 2i by 2 minus 4i. So that's on the top. On the bottom of the complex number, on the bottom of the fraction, we have 2 plus 4i multiplied by its conjugate, 2 minus 4i. Now, I've picked that conjugate specifically because you're going to see in a second what happens when you multiply a complex number by its conjugate. So on top, I'm going to split my first bracket. I'm going to split that first bracket in half, and I'm going to multiply by the second bracket, and I'm going to end up doing exactly the same on the bottom. So on top, I end up getting 4 times the second bracket, which is 2 minus 4i, minus 2i times 2 minus 4i. On the bottom, I end up with 2 times the second bracket, 2 minus 4i, plus 4i times 2 minus 4i. So working out my multiplication, I have 4 by 2 is 8, 4 by minus 4i is minus 16i. Minus 2i by 2 is minus 4i. And be careful here, we have a minus 2i by a minus 4i. So minus by minus gives us plus, 2 by 4 gives us 8, I by I gives us I squared. And we're just going to park that for a second. On the bottom line, multiplying 2 by 2 gives me 4, 2 by minus 4i is minus 8i, 4i by 2 is plus 8i. And again, just be careful, this is the most difficult of the multiplication. Plus by minus is minus, 4 by 4 is 16, I by I again is I squared. So working out the top line, and before I do, I just want to draw your attention to the I squared that's here and the I squared that's here. Remind ourselves of what the question told us. The question told us that wherever we see an I squared, it's equal, it's the same thing as minus 1. So we're going to replace that I squared with a minus 1, and we'll end up doing exactly the same thing with the I squared on the bottom. So let's look at what we have. We have 8 minus 16i, minus 4i on top, and we have a plus 8 times a minus 1. On the bottom, we have 4 minus 8i plus 8i, and we have a minus 16 times a minus 1. All that I've done there is I've replaced the I squared with a minus 1. So that's going to give me on top 8 minus 16i minus 4i. When we put like with like on top, we are getting minus 20i, and plus 8 by minus 1 is minus 8. On the bottom, our minus 8i plus 8i will cancel out. So that's why we multiplied in the first place. That's why we multiplied the complex number by its conjugate. So here, that's why we divided like this. We multiplied its complex number by its conjugate with the intention of the imaginary parts cancelling out. So what we've got is on the bottom 4, and then we have a minus 16 times a minus 1, which gives me a plus 16. So you've ended up with a real number on the bottom. On top, 8, take 8, they're going to cancel each other out. So we end up with minus 20i over 20, which we know is minus 1i. 20 divided by 20 gives me 1. It's a really good habit to get into. Even though this number here doesn't have a real component, it's a very, very good habit to get into to write the real part anyway. So the real part is 0 and the imaginary part is minus 1i. Have a look at what they've asked you in the question. Always make sure you're answering exactly what was asked of you. They told me originally that division, that fraction was equal to 0 plus ki. And we've just worked out that it's equal to 0 minus 1i. So 0 plus ki must be equal to 0 minus 1i. To find what k is, we just look at our imaginary parts. The real parts are both 0 on the left and the right. The imaginary parts, k must equal minus 1. So your answer at the end, k equals minus 1. I'm running out of space there. Okay, so hopefully that makes a little bit of sense. We're bringing in division of complex numbers, we're bringing in multiplication of complex numbers, conjugates, and we're at the end, we're equating complex numbers. We're letting real equals real and imaginary equals imaginary. So we're very quickly going to have a look at another example. This is 2013, and what we have is z. So often you will see the letter z being used in place of x with complex numbers. Z is 4 over 1 plus root 3i, where I squared is minus 1. So we're seeing that coming up in almost every complex numbers question. Verify, so that means show or check, that z can be written in this form instead. So in other words, they're trying to get us to get rid of the fraction up here and rewrite it in this rectangular or Cartesian form where we have a real and an imaginary part. So as I did in the last question, I'm going to write out my question. It's 4 over 1 plus root 3i, and I'm going to multiply above and below by the conjugate of this bottom line. So the conjugate is 1 minus root 3i and 1 minus root 3i. Whatever we do to the top, we do exactly the same to the bottom. So on top, we end up getting 4 times 1 minus root 3i. On the bottom, we end up getting 1 plus root 3i times 1 minus root 3i. Remember, what we're hoping to happen on the bottom is, because we're multiplying a complex number by its conjugate, the imaginary parts should cancel each other out. So on top, 4 by 1 is 4. 4 by minus root 3i is just 4 minus 4 root 3 with an I. On the bottom, we're going to split our first bracket in half, and we're going to multiply our back-to-back brackets. So that's 1 by the second bracket and plus 3i by the second bracket as well. Top line, 4 minus 4 root 3i. Bottom line, we're going to do our multiplication. 1 by 1 is 1. 1 by minus root 3i is minus root 3i. Root 3i by 1 is plus root 3i. And again, be careful as ever with the last one. Root 3i by minus root 3i. So sign by sign, plus by minus gives me a minus. Root 3 by root 3, well, that's just root 3 by itself is root 3 squared. And we know that the square root and the squared cancel each other out. So we're left with just 3. and I by I is I squared. But we know from the last question, and they've told us in the question as well, that I squared, that can be replaced with a minus 1. So reevaluating on top, we have 4 minus 4 root 3i. On the bottom, your imaginary parts cancel out as we expected. We end up with 1 minus 3 by minus 1. So that's 4 minus 4 root 3i over 1 plus 3, 4 minus 4 root 3i all over 4. And as we did at the very start, everything there can be divided by 4. So what we're left with is 1 minus 1 root 3i, or 1 minus root 3i, which is exactly the way they wanted us to show it from the question. Okay, so the big thing to remember with division of complex numbers, how do we do it? We multiply above and below by the conjugate of the denominator, the conjugate of this bottom line here. So hopefully that helps. Again, as I mentioned, the conjugate root theorem is a video that is gone into the live chat. So while we're on this question 2013, we'll also just have a look at part B of the question, which involves plotting the complex number on the Argand diagram and writing it in polar form. Polar form is a very, very popular question in complex numbers, so it's important that we have a look at it. Before we start to answer the question, let's remind ourselves what polar form exactly is. So if we take this complex number, z is 1 minus root 3i from part A. So z was 1 minus root 3i from part A. This is what we call rectangular or Cartesian form. So rectangular or Cartesian form. And that just means it's in the form a plus bi. It has a real and it has an imaginary part. Sometimes we're asked to change it into polar form. So polar form is when we write it in this form, r times the cos of theta plus I times the sine of theta. R is our modulus, or our distance that the complex number lies from the origin. We'll have a look at that on the Argand diagram in a second. And theta is what we call the argument of the complex number. It's basically the angle that the complex number makes with the positive real axis. So the positive real axis. So r is the modulus and theta is the argument or the angle that the complex number makes with the positive real axis. So our first job in part B, before we write it in polar form, is to plot that complex number on the Argand diagram. So as you can see from the diagram beside you, we have a imaginary axis, which is usually known as your y-axis, and we have the real axis, which you will be familiar as your x-axis normally. And we're plotting that complex number 1 minus root 3i. So we start at the origin as normal. We go out 1 out the real axis because that's the part of the complex number. It's the real part, it's 1. And we go minus root 3. Now, root 3 is approximately 1.7. So we're going across here to 1, and we're going down about 1 minus 1.7. So we're talking about roughly, it's not exact, but we're talking about roughly there is where my z is going to be. How did I get there? Well, I went across 1 on the real axis, and I went down root 3 on the imaginary axis because it's about minus 1.7 in or around. Okay. Next, it's always a good idea when we're changing to polar form, it's always a really good idea to plot your complex number. Even if that's just on a rough Argand diagram, plot your complex number, okay? And then we're going to join the complex number back to the origin. So with a ruler, if you have it, you're going to join your complex number back to the origin. We're also going to just complete this triangle here with the real axis. And you'll notice, because I dropped a perpendicular there, that's a right angle. Okay, so our first job to write this complex number in polar form, our first job is to find r our modulus. So again, there is a video link in the chat on how to find the modulus if you're a little bit rusty on that, but you'll be familiar hopefully with your formula. Your modulus is the square root of a squared plus b squared. So where do I get my a and b from? Well, my a is my real part of my complex number. My b is my imaginary part of my complex number. So putting that into my formula, r is the square root of a squared is just 1 squared, and b squared is just minus root 3 squared. So my b is all of that, minus root 3 squared. So I'm putting that into my calculator, square root of 1 squared plus minus root 3 squared, and we should be getting a modulus of 2. So that just means that the distance of that complex number from the origin is a distance of 2. So that red slanted line there has a length of 2. How do we find our theta? So theta is the more awkward one to find. As I mentioned up here, and this is very, very important, it's always the angle that the complex number makes with the positive real axis. So if I just draw in on my Argand diagram, this here is my positive real axis. And I'm looking at the angle that it makes with the positive real axis. And I'm always working anti-clockwise. So I'm starting here and I'm working all the way around to my complex number, which is here. That angle that I've just drawn in, that's my theta. Okay, so this full angle here that I've just drawn in, anti-clockwise from the positive real axis, that's my theta. However, we're going to use our triangle, our right angle triangle down here to try work out what theta is. So I'm going to give this angle here a name. I'm going to call it the angle alpha, or call it A or B or X or Y, whatever you want to call it. I'm going to use my knowledge of trigonometry to find that angle alpha. And before I do, I'm going to just mark in the lengths of these lines here. So this line here is of length 1 because it's 1 across on the real axis. This line down here is of length root 3. I know it's negative, but I'm just talking about the length, so that's why I'm just leaving it as positive root 3. And what I've got now is I have my opposite and I have my adjacent. So root 3 and 1 are my opposite and my adjacent respectively. So to find alpha, I'm going to use tan. Tan of alpha is going to be my opposite, which is root 3 over 1. To find alpha, I need to find the tan inverse of root 3 over 1. So on your calculator, that's shift and tan and root 3 over 1. If your calculator is in radians, which mine is, you're getting an angle of 1/3 pi or pi over 3. And in this question, it hasn't specified, so it doesn't matter if your calculator is in radians or degrees. It has not specified. I'm going to leave mine in radians. So what we've just found is that little angle in there is root 3. But what we need to work out is what this full angle all around here is. So we're familiar with the full circle being 360 degrees or 2 pi radians. We're just this little yellow angle short of 360 degrees or of 2 pi radians, that much short of a full circle. So to find what theta, what my argument is, it's a full circle, which is 2 pi minus my alpha of pi over 3. That should give me an argument or a theta of 5 pi over 3. So we've just found our modulus. We've just found our theta, our argument. Now we're going to put it into our polar form formula. So my complex number z, which in Cartesian form was 1 minus root 3i, that's going to be 2, which is r, times the cos of theta, which is 5 pi over 3, plus I times the sine of theta, which is 5 pi over 3. As I mentioned, my calculator is in radians. The question has not specified, so I can leave my answer in degrees if I rather working with degrees. If you're unsure, and it's always a good idea to check your answer, all you need to do is go back to your calculator and literally type this in. Now, just like you can't put in x's in algebra, you can't put in i's in complex numbers. So you would need to type in 2 times the cos of 5 pi over 3, and that should give you 1, my real part. You would then need to type in 2 times the sine of 5 pi over 3, and that should give you minus root 3, which is your imaginary part. Okay, so for you full members, there's loads more examples of changing to polar form from the exam questions. You'll find those in week 2 of your exam countdown. That's available on TheMathsTutor.ie for our full members. Okay, there's also, as I mentioned already, 2 links to extra additional material in the chat. And we will be back next week with complex numbers 3. So hopefully that was of some use to you, and I hope you can tune in next week.